So I want you to think for a second about something incredibly common, like something you probably see every single day.
Oh, absolutely.
Yeah, maybe you see it at the grocery store or on your kids, or, I mean, maybe you even have it in your own mouth right now.
Right, yeah.
I'm talking about the metal wires in orthodontic braces.
Yep. The classic metallic smile.
Exactly. And at first glance, it looks like just simple, archaic plumbing for the mouth, right? Just little metal tracks and rubber bands.
It really does look basic.
But what if I told you that what looks like a basic wire is actually this secretly sci-fi masterclass in advanced material science?
And biomechanics, too.
Yes, biomechanics and literal space-age metallurgy.
It is genuinely one of the most fascinating examples of engineering hiding in plain sight. I mean, we look at a kid with braces and we just see metal pulling on teeth.
Right.
But the reality of what is happening on a molecular level and an atomic level within that wire, it completely challenges our fundamental, everyday understanding of how solid objects are supposed to behave.
And that is exactly our mission for this deep dive. Today, we are going to completely decode the engineering behind orthodontic arch wires.
It's a huge topic.
It is. We've got a massive stack of sources on the table today. We're talking foundational orthodontic textbooks, historical metallurgical reviews, and some incredibly dense biomechanical research papers detailing the mathematical limits of metal.
Some really heavy reading.
Oh, very heavy. We're going to explore exactly how these materials are categorized, decode the physics of the stress-strain curve, and take a very serious look at the mind-bending martensitic phase transitions.
Which is just wild.
It is. It's the mechanism that allows a piece of metal to literally remember its own shape.
Which is a phenomenon that completely rewrites the rules of classical mechanics that most of us learned in high school physics.
It totally does. So whether you have worn braces, you're currently paying for your kids to wear them, or you're just insanely curious about the hidden engineering in everyday life, this deep dive is going to completely change how you view a simple wire.
I guarantee you'll never look at them the same way again.
Okay, let's unpack this. Let's start with the absolute basics of the mechanical system.
Good place to start.
What exactly is this wire doing inside the mouth from a purely structural standpoint?
Well, functionally speaking, when you place an orthodontic arch wire into a patient's mouth, you are basically installing a specialized beam.
A beam, like in construction.
Exactly like in construction. In engineering terms, it acts as either a cantilever beam or a supported beam.
Okay, break that down for me. What's a cantilever beam?
So a cantilever beam is supported on only one end. Think of like a diving board.
Okay.
Or in the mouth, maybe a small spring poking out of a specialized appliance just to push on a single molar in the back.
Got it. And the supported beam.
More commonly, the arch wire acts as a supported beam, which means it spans between two brackets on adjacent teeth.
Right, so it's anchored on both sides.
Exactly. And the sole purpose of this beam, I mean, the entire reason it exists, is to apply a mechanical force to move teeth through bone.
Moving teeth through solid bone. I mean, when you say it out loud, it sounds kind of barbaric.
It does sound intense.
And to do that safely, without just ripping the tooth out of the socket or completely destroying the root, you must have an absolute granular understanding of how the material of that beam behaves when you bend it.
The biological stakes are incredibly high here. You can't just guess.
Right.
Because if you apply too much force, you actually crush the blood vessels in the periodontal ligament.
Oh, wow.
Yeah, you starve the tissue of oxygen, and the bone remodeling process just stops dead in its tracks.
So the teeth stop moving altogether.
Exactly. It's called hyalinization. So the margin for error is razor thin.
That's terrifying.
It is. So to understand how doctors control that force, we have to look at the foundational concept of material elastic behavior.
Okay.
In engineering and materials science, we visualize this using what's called the stress-strain diagram.
The stress-strain diagram.
Yes. This is basically the ultimate blueprint for how any material responds to an external load.
Okay, we definitely need to define those two terms, stress and strain, because they sound like synonyms in everyday language, right?
They do, yeah.
Like, we use them interchangeably to talk about our jobs or, our commute. But in physics, they describe two very distinct parts of an interaction.
Yeah, they describe the invisible cause and the visible effect.
Okay, I like that. Invisible cause, visible effect.
So stress is the internal distribution of the load.
Meaning what, exactly?
It is defined mathematically as the force per unit area. It's usually measured in megapascals, or MPa.
Megapascals.
You can think of stress as the internal pressure. It's the mechanical tension the atomic bonds inside the metal are actually feeling when a force is applied.
Okay, so stress is what the atoms are feeling.
Yeah.
What about strain?
Strain, on the other hand, is the internal distortion produced by that load.
The visible stretch.
Exactly. It's the deflection per unit length. So basically, stress is the invisible force pushing or pulling on the atomic bonds, and strain is the physical, measurable stretching or bending that results from that stress.
Stress is the invisible push. Strain is the visible stretch. I think I've got it.
Perfect.
So if we imagine graphing this out, like tracking the visible strain against the internal stress as we bend a wire, we generate a curve.
Yes, a very specific curve.
And that curve gives us the vital statistics of the metal.
It tells us everything we need to know.
So exactly what properties are orthodontists pulling from this data?
Well, from that curve, we derive 3 major clinical properties that really dictate whether a wire is actually useful in a biological setting.
Okay, what's the first one?
First, we look at stiffness.
Stiffness, yeah.
Yeah. On a stress strain graph, the initial part of the line goes up at an angle.
Right.
The slope of that linear elastic portion represents the stiffness. And this linear relationship is governed by Hooke's law.
Okay, so a steep slope means what?
A very steep slope means it takes a massive amount of stress to generate even a tiny bit of strain.
So it's super rigid.
Exactly. That's a highly stiff, rigid material. Conversely, a flatter slope means the material is flexible. A small amount of stress creates a lot of strain.
Got it. Okay. Property 1 is stiffness. What is the second piece of the puzzle?
The second is range.
Range, like how far it can go.
Basically, it's the maximum distance a wire can bend elastically before it deforms permanently.
Okay.
If you keep bending a wire, eventually you hit a point where it just stops bouncing back to its original shape.
It stays bent.
Right, it yields. Clinically, this is often measured at the 0.1% yield point.
The 0.1% yield point.
Yeah, that's the exact mathematical moment where 0.1% of the deformation becomes permanent. The distance you can bend it up to that exact point is the range.
So range is basically how far I can pull it before I ruin the spring.
That's a great way to think of it.
Like if I bend it and it snaps back perfectly straight, I'm working within the range.
Yep.
But if I bend it too far and it stays a little bit crooked, I've exceeded the range.
That is the perfect way to visualize it. And that brings us to the third major property, which is strength.
Strength. Okay, how do we calculate that?
Mathematically, strength is simply stiffness multiplied by range.
Oh, it's just the two combined.
Yeah, it represents the absolute maximum load the wire can sustain before yielding.
Okay. Now, the biomechanical research we're reviewing today also emphasizes 2 other terms:
Which ones?
resilience and formability. How do those fit into this picture?
So resilience is a measure of the energy storage capacity of the wire.
Energy storage.
Yeah, if you look at the area under that linear bouncing back part of the curve, that total area represents the resilience. It's an aggregate of both the strength and the springiness.
Okay. And formability.
Formability, conversely, is what happens past the yield point.
So once it's already permanently bent.
Exactly. Once you've permanently bent the wire, how much more permanent bending can it take before the atomic bonds just give up and the wire physically snaps in half?
Like bending a paperclip back and forth until it breaks.
Exactly like that.
So we have stiffness, range, strength, resilience, and formability.
A lot of variables.
Right. But let's bring this out of the laboratory and back to the patient sitting in the chair.
Always a good idea.
Why does the doctor care about this specific combination of variables?
Because the biological requirements of moving teeth are highly contradictory.
Contradictory how?
Well, if strength were the only factor that mattered, they would just use a thick piece of industrial rebar in your mouth.
Right, which would be terrible.
Obviously. An ideal orthodontic wire needs an almost impossible combination of traits.
Like what?
It needs high strength so it doesn't permanently deform the second the patient bites down on a piece of tough bread or a carrot.
That makes sense.
But simultaneously, it needs low stiffness.
To keep the force gentle.
Exactly. So it delivers a gentle, continuous, biologically safe force to the tooth root rather than a jarring, painful jolt.
Right.
It also needs high range so the doctor can thread it through teeth that are wildly out of alignment without the wire staying permanently kinked.
Hmm.
And finally, it needs high formability, so the orthodontist can bend intricate custom loops or stops into the wire without it snapping in their pliers.
Okay, I want to push back on this a little bit.
Go for it.
Let's think about this mechanically. Like comparing a thick steel cable to a bungee cord.
Okay.
A steel cable is immensely strong, but its stiffness is off the charts. Like, it has virtually zero range.
True.
But a bungee cord has incredible range and very low stiffness, but its strength is terrible.
Right, it can't hold up a bridge.
Exactly. So if stiffness is really just a function of how the material resists bending, why can't we just use a standard steel wire but make it incredibly microscopically thin?
Like hair thin.
Yeah. Wouldn't reducing the diameter give us all the flexibility and range we need to fix severely crooked teeth without needing to invent entirely new metals?
The logic makes perfect sense on the surface.
Thank you.
But when we dive into the foundational mathematical models, specifically looking at the detailed mechanical analysis in the source materials, we run into the hard limits of physics.
The hard limits of physics. Ruining my brilliant idea.
I know, I'm sorry, but when you decrease the diameter of a round wire, you absolutely do increase its springiness.
Okay, so I was half right.
You were. In fact, the math shows that springiness increases by an inverse fourth power function of the diameter.
Oh, wow. Let me do that math really quickly.
Sure.
If I take a wire and I cut the diameter in half, it doesn't just get twice as springy. 2 to the 4th power, it gets 16 times springier.
It does. It gets incredibly springy.
That's a huge jump.
So on the springiness front, your hair-thin wire idea is brilliant.
But there's a catch.
There is a fatal flaw.
Let's hear it.
The mechanical analysis also demonstrates that as you decrease the diameter, the strength of the wire decreases by a cubic function.
A cubic function.
Yeah. So if you cut that diameter in half to get your 16-fold increase in springiness, the wire simultaneously becomes 8 times weaker.
Oh, wow. The Strix just falls off a cliff.
It completely collapses.
That's brutal.
It is. The strength drops so rapidly that long before your thin steel wire becomes flexible enough to reach a severely displaced sideways incisor, it becomes fundamentally too weak to withstand the basic occlusal forces of human chewing. Meaning the patient would bite down once, the hair-thin wire would instantly exceed its yield point, deform, and stay permanently bent.
Making it totally useless.
Exactly. The geometry of a metal beam has absolute mathematical limitations.
You can't just cheat the math.
You really can't. And this realization forced a massive pivot in the field.
Because they couldn't just change the shape anymore.
Right. Since manipulating the physical dimensions of the wire couldn't solve the biological problem, scientists realized they had to start manipulating the chemistry of the metal itself.
Which takes us out of basic physics and squarely into the evolution of alloys.
It does.
Because if geometry fails you, metallurgy has to save you.
That's exactly what happened.
And his evolutionary journey starts, surprisingly enough, with jewelry.
It really is a fascinating origin story.
Tell me about it.
If you read the historical reviews of the profession, you see that in the early 20th century, the pioneers of orthodontics were relying almost entirely on precious metals.
Precious metals.
Yeah, we are talking about extensive use of gold alloys, often mixed with platinum, palladium, and copper.
Having a mouth full of heavy gold appliances sounds incredibly opulent.
Very fancy.
But from a purely engineering perspective, why gold? Like, why not iron or brass?
Honestly, it was a matter of survival.
Survival of the metal.
Yes. The human mouth is an aggressively hostile environment for a metal.
I guess I'd never thought about it like that.
Oh, it's terrible. It is constantly wet. The temperature fluctuates wildly depending on what you are eating or drinking, like hot coffee, then ice water.
Right.
And it is full of highly reactive digestive enzymes and varying acidic pH levels.
It's basically a vat of acid.
It is an engine of corrosion.
Okay, so gold was the only thing that could handle that.
Yeah. At the time, yes. Gold alloys were the only materials sophisticated enough to survive intraorally for months or years without oxidizing, rusting, and degrading into toxic byproducts.
Because nobody wants toxic rust in their mouth.
Definitely not. But as the historical texts extensively document, gold had massive biomechanical drawbacks.
Because it's soft. Right?
Exactly. Gold is fundamentally a soft metal. Even when metallurgists alloyed it with platinum and copper to toughen it up, the yield strength was pitifully low.
So it would just bend and stay bent.
Yep. The springiness was practically non-existent, and the financial cost was, frankly, astronomical.
I can imagine.
So the early practitioners were stuck with a wire that was wildly expensive, too soft to hold its shape, and required constant replacement or manual readjustment just to keep the teeth moving.
That sounds like a nightmare for the patient and the doctor.
It was incredibly tedious.
What finally broke them out of the gold standard?
The absolute watershed moment was the introduction of 18/8 stainless steel.
18/8 stainless steel.
Yeah. This material completely revolutionized the field. It entirely replaced gold because it offered vastly superior yield strength, significantly better springiness, and crucially, an equivalent, if not superior resistance to the corrosive oral environment.
Let's break down that specific recipe, 18/8 stainless steel.
Sure.
What do those numbers actually represent, and why does that specific blend survive the mouth so well?
So the numbers are the exact metallurgical composition. It's 18% chromium and 8% nickel, added to the iron and carbon base.
18% chromium, 8% nickel. Okay.
The chromium is the absolute magic ingredient for corrosion resistance.
What does the chromium do?
When chromium is exposed to oxygen, it reacts instantly to create a microscopic passive oxidation layer on the surface of the wire.
Like a shield.
Exactly like an invisible self-healing shield. It completely isolates the underlying iron from the moisture and acids in the mouth, preventing rust entirely.
That's incredibly cool. And the nickel.
The 8% nickel is then added to increase the ductility of the alloy.
Ductility. Meaning what?
Meaning the metal can be drawn through dies into extremely thin wires without the atomic structure shattering.
Ah, so it won't just crumble when they try to make a wire out of it.
Right.
So metallurgy gives us a material that won't rust and won't shatter.
A huge upgrade from gold.
But steel is still notoriously stiff.
Yeah.
I mean, we just talked about how you can't make it paper thin without losing strength.
Right, the cubic function problem.
So how did orthodontists in the mid-20th century manage to get the flexibility they needed out of a fundamentally rigid material like steel?
This is where the sheer craftsmanship of early orthodontics really shines.
Craftsmanship.
Yeah, they learned to manipulate the crystalline structure of the steel through temperature and physical stress.
Wait, they were altering the crystals.
Oh yeah. Let's look at the concept of annealing.
Annealing, okay.
If you take a piece of stainless steel and heat it up to a very specific high temperature, and then let it cool down very slowly, you are imparting thermal energy to the atoms.
Like baking it.
Basically. This allows the tangled atomic crystal planes to relax and reorganize into a lower energy, highly uniform state.
And what does that do to the wire?
The resulting wire becomes dead soft.
Dead soft.
Yeah, it is highly formable and has almost no springiness at all.
So you could tie a knot in it.
Easily. Now, a dead soft wire is completely useless for actually moving teeth because it has no range.
Right, it won't pull back.
Exactly. But it is absolutely perfect for manufacturing the tiny, intricate ligature wires that orthodontists use to tie the main arch wire firmly into the brackets.
Oh, those little wires that wrap around each tooth to hold everything together?
Precisely.
So they use the heat-treated relaxed steel to tie the system together.
Yeah.
But what do they do to the main wire to make it strong enough to actually move a tooth?
For the main arch wire, they do the exact opposite. They utilize a process called cold working.
Cold working, so no heat.
No heat. By physically drawing, straining, and rolling the metal at room temperature, they are actively forcing the atomic crystal planes to slide past one another.
Just brute forcing the atoms.
Exactly. As these planes slip, the imperfections, the dislocations in the crystal lattice collide and get tangled up.
Like a microscopic traffic jam.
That's the perfect analogy. Because the atoms are jammed together, it becomes exponentially harder for them to slide past one another the next time a force is applied.
So it makes the wire harder.
It hardens the wire immensely, creating what they call super or extra hard grades of steel with incredibly high yield strength.
Okay, so it's super strong now.
Yes.
Yeah.
The major trade-off, however, is that this tangling heavily reduces formability.
Because the traffic jam is already so packed, you can't move anymore.
Exactly. If a doctor tries to take a pair of pliers and bend a severely cold-worked steel wire too sharply, the lattice just can't yield and the wire physically fractures.
It just snaps.
Right in half.
Wow. So they are playing this incredibly delicate game of manipulating the crystal lattice.
It's high-level physics in a dental office.
But even with cold working, if the patient has really crowded teeth, A stiff steel wire is going to deliver a painful amount of force,
Yep,
right?
absolutely will.
So how did they bridge that gap before modern alloys existed?
Well, they turned to structural geometry.
Okay.
Since the math proved they couldn't just use a single microscopic wire, they started weaving them.
Weaving them.
Yeah. They realized that the stiffness of a beam isn't just about its total diameter, it's about how the contiguous mass of metal resists bending.
I see where this is going.
If you take two extremely thin 10 mil steel wires and weave them together into what they called a twin wire,
Okay.
or if you twist 3 or 6 microscopic strands into a braided cable, you achieve this amazing mechanical compromise.
Because they're separate strands.
Right. You get the combined tensile strength of a much thicker wire, meaning it won't permanently deform when the patient chews. But because the individual strands can microscopically slip and slide past each other when the whole cable is bent, you maintain the independent flexibility and lower stiffness of the smaller wires.
That is brilliant engineering.
It really is.
It's exactly the same principle as a suspension bridge cable, isn't it?
Spot on.
Like, you don't use a single solid column of steel to hold up the Golden Gate Bridge. You spin thousands of small wires together.
Exactly.
It has the immense strength to hold the roadway, but the flexibility to sway in the wind without snapping.
Precisely. The braided steel wire was a massive leap forward for the profession.
But let me guess, it wasn't enough.
It wasn't. Eventually, even multi-strand steel hit its biological limits.
Why?
It is strong, yes, but it still fundamentally lacks the massive elastic range needed to engage wildly displaced, severely crowded teeth without applying heavy forces that risk root resorption.
Right, because it's still steel at the end of the day.
Right. The field had pushed steel as far as it could geometrically go. They needed a bridge material, an intermediate step between the soft gold of the past and the rigid steel of the present.
Which brings us to the early 1980s and the introduction of a material that filled that exact void.
Yes.
Beta titanium.
Yes, beta titanium. Although in the clinical orthodontic world, you will almost exclusively hear it referred to by its commercial acronym, TMA.
TMA.
What does that stand for?
It stands for titanium molybdenum alloy.
Titanium molybdenum alloy. Got it. The introduction of TMA filled a massive, glaring gap in the biomechanical toolkit.
Let's look at its specific properties.
Mm-hmm.
Where does TMA sit on that stress-strain curve we talked about earlier, compared to our Coldworks stainless steel?
It sits perfectly in the middle, which is exactly why it is so valuable.
Okay.
When you analyze the curve, TMA has roughly half the yield strength of stainless steel.
Half the strength?
Yes. But crucially, it has significantly lower stiffness, massive range, excellent resilience, and unlike Coldworks steel, it maintains fantastic formability.
Meaning the doctor can bend it sharply without breaking it.
Exactly.
So it sacrifices some raw strength to gain a huge amount of flexibility while still allowing the orthodontist to customize it.
You've got it.
How does that translate to the patient's treatment?
Well, it makes TMA the ultimate finishing wire.
Finishing wire, meaning at the end of treatment.
Exactly. Towards the end of a patient's treatment, the teeth are generally straight, the big gaps are closed, but the bite isn't perfect.
So they need to tweak it.
Right. The orthodontist needs to do fine-tuning, inserting what are called artistic finishing bends.
Artistic bends. I like the sound of that.
For example, the crown of the tooth, the part you see, might look straight, but the invisible root underneath the gums might be angled wrong.
Ah, okay.
To fix that, the doctor has to twist the wire to apply torque to the root.
They have to physically twist the metal to angle the root.
Right. If you try to twist a thick, stiff stainless steel wire and jam it into the bracket to torque a root, the stiffness is so high that it will deliver a massive, potentially destructive biological force to the bone.
Because steel doesn't want to bend.
Exactly. But with TMA, the orthodontist can bend those same intricate, highly customized loops to perfectly position the root.
And it's safer.
Much safer. Because the stiffness is naturally lower, the wire delivers a much lighter, safer, more continuous force.
Okay, I think I'm seeing the whole chessboard here.
It's all about having the right tool for the job.
Steel is the brute force material. It's the sturdy, unyielding track. Beta titanium is the sculptor's clay, giving the doctor the ability to make delicate, artistic finishing touches with safe biological forces.
That's a great summary.
But wait, there is still a massive piece of the puzzle missing here.
Oh.
Neither of these materials explains the hardest part of braces.
Which is?
How do you take a mouth on day one, where the teeth are completely sideways, wildly overlapping like high up in the gums, and just untangle them in a matter of months.
Right, the initial alignment phase.
Yeah. If you put steel in there, it's too stiff.
Way too stiff.
If you put TMA in there, it doesn't have enough range for that level of chaos.
It doesn't.
So what do they use?
This raises an important question. How do you achieve massive, extreme mechanical deflection while maintaining a light, continuous, biologically safe force? And the answer to that question did not come from dentistry. And it didn't come from metallurgy labs studying jewelry either.
Where did it come from?
It came from the aerospace industry.
Here's where it gets really interesting.
Oh, it really is.
We are leaving the realm of standard metals that just bend and stretch, and we are entering the world of phase-shifting crystals. Let's talk about the space-age miracle, nickel titanium.
Nickel titanium, universally referred to as nitty or nitinol.
Didn't know.
Yes, it is arguably the most significant material science breakthrough in the history of orthodontics.
That's a big claim.
It's true. It was originally developed by the Naval Ordnance Laboratory for the space program and military applications.
Wait, the military developed braces?
Not intentionally, but the name nitinol actually stands for Nickel Titanium Naval Ordnance Laboratory.
That's what it means.
Yep. Its exact composition is generally around 52% nickel, 43% titanium, and roughly 3% cobalt to tweak the properties.
Okay, so it's a very specific blend.
It is, but the chemical recipe isn't the magic part.
What's the magic part?
What makes this alloy a literal miracle in biomechanics is that it possesses two entirely distinct, reversible crystalline structures.
We need to pause on that because that is a profound concept.
It is.
Most metals just have one way their atoms stack together, right? Like iron is iron.
Exactly. Most metals have a single, stable crystal lattice.
Right.
But niti is polymorphic. It can exist in two distinct phases depending on the energy in the system.
Two different phases.
The first phase is called austenite.
Austenite.
Yeah. This is a highly ordered, simple, rigid, cubic atomic structure. It is the phase the metal prefers at higher temperatures and lower physical stress.
Okay, rigid cubes, got it.
The second phase is called martensite.
Martensite.
Right. This is a much more complex, folded, highly pliable monoclinic or hexagonal atomic structure.
Okay.
And it is the phase the metal prefers at lower temperatures or when subjected to high physical stress.
Okay, so this one piece of metal has two different atomic skeletons.
Yes.
It can be a rigid cube or a pliable hexagon.
Exactly.
Why is that shifting skeleton so revolutionary for straightened teeth?
To understand the revolution, we have to contrast it with how normal metals behave when bent.
Let's go back to our cold-worked stainless steel wire.
Perfect. When you bend a steel wire, you are physically pulling the atomic bonds apart. You are stretching the distance between the iron atoms.
That's Hooke's law in action, right?
Exactly. If you pull too hard, the atomic bonds slip past their yield point, the planes shear, and the wire is permanently bent.
Because you stretched them too far.
Right. But nitty fundamentally bypasses Hooke's law.
Bypasses it.
It doesn't just stretch its bonds. When you apply massive stress to an austenitic nitty wire, say, by twisting it severely to tie it to a completely sideways tooth, the internal atomic lattice doesn't stretch and break.
What does it do?
It physically, geometrically rearranges itself.
Wait, the atoms physically move?
Yeah, they literally shift their positions. They fold into the pliable martensitic phase to accommodate the load.
I love this concept.
It's wild, isn't it?
It's exactly like a transformer toy.
A transformer.
Yeah. It doesn't just bend under pressure. When it gets stressed, it folds its molecular arms and legs into an entirely different geometric vehicle mode to absorb that stress.
That's actually...
And when the stress is finally removed, it morphs back into the robot. No pieces are broken, no bonds are snapped, just geometry shifting back and forth.
That analogy perfectly captures the mechanics of a martensitic phase transformation.
It makes so much sense now.
It is entirely reversible. The atomic bonds aren't slipping or breaking, they're just twinning and folding.
Unbelievable.
And the seminal papers that brought this into orthodontics detailed how this stress-induced reversible martensitic transformation creates a completely unique mechanical property.
What's it called?
It's called superelasticity, or sometimes it's referred to in the literature as pseudoelasticity.
Superelasticity. It sounds like a comic book superpower.
It basically is.
How does superelasticity change the shape of that stress strain graph we talked about at the beginning?
This is where nitty breaks the traditional rules of physics.
Okay.
On a stress strain graph, a normal metal like steel goes up at an angle, More deflection equals more force. It's a linear proportional relationship.
Right. If I pull harder, it pulls back harder.
Exactly. But a superelastic needy wire has a massive horizontal flat loading and unloading curve.
Flat.
Yes. Once the stress triggers the phase shift from austenite to martensite, you can continue to bend the wire further and further, increasing the strain massively.
Okay.
But the stress, the internal force, remains perfectly flat.
A completely flat curve. What does that actually mean for the biology of the patient? Like, why should a doctor care about a flat curve?
Because a flat curve translates clinically to constant force.
Constant force.
Imagine a patient with two crooked teeth. Tooth A is just 1 millimeter out of perfect alignment.
Barely crooked.
Right. The doctor ties a nitty wire to it. The wire bends slightly, enters the superelastic plateau, and applies a gentle, biologically ideal 50-gram force to pull it into line.
50 grams, got it.
Now imagine tooth B, which is a massive 5 millimeters out of place.
Totally sideways.
Yeah. The doctor has to severely distort and bend the wire to reach it.
Okay.
If they used steel, bending it 5 times further would generate 5 times the force.
Which would crush the ligament.
Exactly. It would crush the periodontal ligament, stop blood flow, and cause severe pain.
Ouch.
But with superelastic needy, because the crystal structure just keeps shifting deeper into the martensitic phase to absorb the strain, it applies the exact same gentle 50-gram force.
Wait, really?
Really, whether the tooth is 1 millimeter out of place or 5 millimeters out of place, the force delivered to the root is identical, constant, and perfectly safe.
That is truly bordering on magic.
It's pure science.
But it feels like magic. It completely severs the linear link between how far you bend the wire and how hard it pulls back.
That's the beauty of it.
It's a biological failsafe built directly into the atomic structure of the metal.
It is the absolute holy grail for the initial alignment of teeth. It provides a light, continuous force over a massive range of activation, allowing the bone to remodel optimally without necrosis.
But the magic trick doesn't stop with just bending the wire, does it?
No, it doesn't.
Because this phase shift, this jump between austenite and martensite, isn't just triggered by mechanical stress, right?
Correct.
It's also uniquely sensitive to thermal energy.
Heat and cold.
Which brings us to the concept of thermoelasticity, or wires with a memory.
Yes. While superelasticity is the phase shift triggered by mechanical stress, there is a sister phenomenon inherent to nitty known as sheet memory, or thermoelasticity.
Memory.
This is the transition between the martensite and austenite crystal structures triggered entirely by changes in temperature.
Okay, let me paint a picture of how this actually looks in a modern orthodontic clinic.
Please do.
Because visualizing the clinical workflow is what finally made the physics click for me.
It really helps.
So imagine you are sitting in the chair on day one. Your teeth are incredibly crowded.
Total chaos.
Right. The orthodontist takes a shape memory nitty wire, and before putting it in your mouth, they spray it with a literal freezing agent.
Usually a tetrafluoroethane cold spray.
A cold spray. Immediately, the wire becomes completely soft, dead, and entirely pliable.
Yep.
It has zero springiness. It's like a wet noodle.
Exactly.
Why? Because the extreme cold has stripped the thermal energy from the system, forcing the metal entirely into the folded, pliable martensitic phase.
The clinical term is that the wire is completely deactivated.
Deactivated. So the doctor takes this limp piece of metal string and easily threads it through all the wildly crooked brackets.
No forcing it.
Right. There's no pushing, no fighting the wire, no cane for the patient. They tie it in completely passively.
Light and easy.
But then as you sit there, your natural 98.6-degree body heat starts to bathe the metal.
The mouth is very warm.
The thermal energy transfers into the wire. And as it hits body temperature, the wire wakes up.
I love that phrase, wakes up.
The heat provides the energy necessary to trigger the atomic transition back to its rigid, ordered, austenitic crystal structure.
The rigid cubes.
Yes. And as those atoms snap back into their cubic lattice, the wire perfectly remembers its original ideal U shape.
It remembers.
It slowly stiffens, gently but persistently dragging your crooked teeth with it as it returns to its factory setting.
It is a phenomenal, elegant clinical tool.
It really is.
And the specific thermodynamics of this process have been beautifully detailed in the orthodontic literature. They rigorously explored what is called the temperature transition range, or TTR.
Okay, TPR.
The true genius of modern metallurgy is how manufacturers have learned to hack this transition temperature.
How?
They don't just use standard nitinol anymore. They add copper to the alloy, creating what is known as copper nitty.
Copper.
By meticulously tweaking the percentage of copper, they can precisely dial in the transition temperature to match exact human body temperature.
Oh, wow. So they are customizing the chemistry of the alloy. So the wake-up point, the shift from martensite to austenite, happens exactly at 98.6 degrees Fahrenheit.
Exactly. They tuned it perfectly to the human body.
That is insane.
It's amazing. And the thermodynamic research also highlighted another crucial phenomenon in these memory wires called hysteresis.
Hysteresis. It sounds like a complicated physics concept.
A little bit.
How does it apply to a wire in a patient's mouth?
It's a term that describes the energy loss during the phase transition.
Energy loss.
In practical terms, it means that the loading curve and the unloading curve on our stress-strain graph do not perfectly overlap.
Okay, meaning what?
It takes more force to trigger the transformation into martensite than the wire gives back when it transforms back into austenite.
So it's not a perfect one-to-one exchange.
Right. Clinically, the orthodontist might have to push a little hard to engage the wire into the bracket. That's the higher loading force.
Right.
But due to hysteresis, the wire pushes back on the tooth to move it with a much lower, dampened, biologically safe unloading force. It's an additional layer of biological protection built right into the thermodynamics of the alloy.
Okay, so we've established that these shape memory, superelastic, phase-shifting, copper-nickel-titanium wires are essentially perfect.
They were incredibly advanced.
They apply gentle, continuous force, they remember their ideal shape, they use body heat to activate, and they have built-in fail-safes to prevent root damage.
All true.
So I have to ask a very practical question.
Go ahead.
If copper nitty is the ultimate miracle material, why doesn't the orthodontist just snap one perfectly customized copper nitty wire in on day one and just leave it there for the entire 2 years of treatment?
That's a very logical thought.
Right. Why is the patient coming in every 6 weeks to get wires constantly swapped out?
That is the million-dollar question. And it transitions us into the absolute core of orthodontic strategy.
Which is?
The clinical choreography.
Clinical choreography. I like that.
Why do we need a massive toolkit of different alloys instead of just one magic wand? The answer lies in the sequential biomechanical phases of orthodontic treatment.
Phases.
Yes. The seminal research outlines exactly why matching the specific metallurgical properties of an alloy to the specific biological phase of treatment is critical for success.
Let's walk through that timeline.
Sure.
Let's assume a standard 2-year treatment. Phase 1 is always initial alignment.
Phase 1 is the chaos phase.
The untangling.
Exactly. The goal is strictly untangling the mess. The teeth are rotated, they are high up in the gums, they angled sideways.
Wow.
For this specific phase, you absolutely must use nitty. Its superelasticity, its shape memory, and its massive range are the only things capable of engaging that level of displacement with light, continuous forces.
Because a steel wire would permanently deform or break the bone.
Exactly. Nitty simply wakes up and gently levels the playing field.
Okay, so after a few months of nitty, phase 1 is done.
Yep.
The teeth are now basically straight, standing side by side in a nice level arch.
They look pretty good.
But maybe there are still big gaps between them. Like if the patient had to have a premolar extracted to make room.
A very common scenario.
So we enter phase 2, the working phase or space closure.
In phase 2, the biological goal changes entirely. You are no longer trying to untangle teeth. You are trying to slide a tooth, racket and all, horizontally along the archwire to close a gap.
Dragging it across the track.
Exactly. And this is exactly where you must completely abandon the miracle of nitty.
Wait, abandon it entirely?
Entirely. And switch back to our old, rigid friend, stainless steel.
But why? Because despite all its space-age magic, nitty is absolutely terrible for sliding mechanics.
Terrible.
Why is it terrible? It's a smooth metal, isn't it? Shouldn't a bracket just glide across it?
It's not about the smoothness. It's about the rigidity and the physics of friction and binding.
Friction and binding.
When you are sliding a tooth horizontally, the archwire acts as a physical track. Because nitty is so incredibly flexible and super elastic, when the orthodontist applies a force to drag the tooth sideways, the wire bows and bends under the pressure inside the bracket slot.
Because it's trying to be flexible.
Exactly. As the wire bows, it loses its straight trajectory, the wire hits the sharp internal corner of the bracket, and it binds.
It gets stuck.
The tooth literally digs a notch and gets stuck in the microscopic bend it just created in the wire.
So the very thing that makes nitty amazing, the fact that it effortlessly bends to absorb stress, creates a literal speed bump for the tooth when you try to slide it.
Exactly. It's too flexible to act as a monorail.
That makes total sense.
Stainless steel, on the other hand, is a highly cold-worked, incredibly rigid material.
It doesn't bow.
It does not bow easily. It acts like a sturdy, unbending steel monorail track.
Right.
The tooth can slide smoothly horizontally along it without the wire deforming and creating binding angles.
Okay, so rigid is good for sliding.
Yes. Furthermore, there is a massive issue of microscopic friction.
Microscopic friction.
The exhaustive tribological studies in the literature investigated the microscopic surface roughness of these different alloys.
Okay, what did they find?
They conclusively found that stainless steel has a dramatically lower coefficient of friction than any titanium-based alloy.
So steel is actually slicker.
Much slicker. Titanium alloys, including nitty and TMA, tend to be microscopically rougher and more chemically reactive at the surface, which causes the bracket to drag and stick.
So the choreography is incredibly deliberate.
Very much so.
Phase 1. You use the flexible magic of nitty to untangle the teeth. Phase 2. You swap it out for the rigid, low-friction steel monorail to slide the teeth and close the gaps.
Perfect summary.
What about Phase 3?
Phase 3 is finishing and detailing.
Okay.
The teeth are untangled, the big extraction spaces are closed, but the bite isn't quite locking together perfectly.
The artistic phase.
Exactly. You need those final millimeter-precise artistic adjustments. You need to torque a specific root or detail the angle of a single crown. As we discussed earlier, this final phase is where beta titanium, or TMA, shines.
Because it's the middle ground.
Yes. It gives the orthodontist the ability to bend in exact, rigid, customized instructions like they could with steel, but because of its lower stiffness, it delivers that final instruction to the bone with a much gentler, safer force.
Drastically reducing the risk of root resorption right at the finish line.
You've got it.
So what does this all mean for the listener?
Well, if we pull all the way back and connect this to the bigger picture.
Okay.
It means that the public perception of orthodontics as just tightening braces is fundamentally wrong.
Yeah, that phrase seems super reductive now.
It really does a disservice to the extreme level of science at play here. It is a highly choreographed, biologically driven sequence of swapping out specific metallic crystal structures.
That's crazy.
A clinician starts with a shape memory, space-age alloy to harness ambient body heat for gentle alignment.
Right.
They then transition to a high-friction, rigid, cold-work steel monorail for gross horizontal movement. And they finish with a specialized titanium-molybdenum blend for delicate, artistic root torquing.
Just tightening wires.
Right. They are not just tightening a wire. They are actively matching the exact mechanical and thermodynamic properties of a metal to the biological requirements of the bone remodeling process at that specific month in time.
That is just incredible. To think that all of that invisible choreography, all of that manipulation of atomic crystal lattice structures and mathematical coefficients of friction is happening quietly inside the mouth of a teenager complaining about eating soup.
It really is a marvel.
So, to summarize our massive journey today,
It's been quite a ride.
we started with the basic physics of a metal beam, understanding how stress and strain, stiffness and range define exactly what a wire can and cannot do to bone.
Yep.
We watched the evolution of the field from the soft, expensive failures of gold alloys to the robust, rust-proof, cold-worked reliability of 18/8 stainless steel.
A huge leap forward.
We saw how beta titanium filled the gap as the perfect, flexible sculptor's clay for those final artistic finishes.
Right.
And finally, we unpacked the borderline magical, space-age martensitic phase shifts of copper-nickel titanium, where your own body heat triggers a crystalline memory to gently and safely untangle a smile.
It is a brilliant, lying timeline of material science.
It really is.
But you know, the field isn't static.
Oh, there's more.
To leave the listener with one final provocative thought from the absolute cutting edge of the source material,
I'm ready.
researchers and metallurgists are not stopping at copper nitty.
What's next?
They are currently developing and testing what are called graded thermodynamic wires.
Graded thermodynamic wires. What does that mean in practical terms?
Imagine a single, continuous piece of shape memory archwire.
Okay.
But during the complex manufacturing process, it is engineered and heat-treated so that its crystalline transition temperature, the point where it wakes up and shifts from martensite to austenite, varies along its length.
Wait, so different parts of the exact same wire wake up at different temperatures?
Precisely. Or, more practically, they react to the exact same 98.6-degree body heat with different levels of stiffness depending on where they sit in the mouth.
Oh, wow.
This means a single, unbroken wire could deliver a highly delicate, very light force to the tiny, fragile lower front incisor teeth.
Because they don't need a lot of force.
Right. While simultaneously delivering a heavy, robust, rigid force to the massive molar teeth in the back of your mouth.
Because they have huge roots.
Exactly. All from the exact same piece of metal, simply reacting to the ambient heat of your body based on how its internal crystal lattice was microscopically graded in the factory.
That is absolutely mind-blowing, customizing the atomic phase shift inch by inch across a single piece of wire to perfectly match the anatomy of different teeth.
It's the future of the field.
Well, that brings us to the end of today's truly massive deep dive. Thank you so much for joining us and exploring the hidden science of everyday things.
Thanks for having me. It was a blast.
Remember, the next time you look closely at a metallic smile, don't just see plumbing. You're looking at a living timeline of space-age metallurgy, phase-shifting crystals, and a true marvel of modern material science.